Hello everybody, today we are going to be proving the absolute convergence theorem, which states that if the series of absolute value of AK converges, then the series of AK will also converge. I know it's been a long time since I made a video, but I just had this question on an exam and I thought, I might as well just make a video on it as well, just to show how it's done, or at least try and show how it's done. So before we start, actually, I would like to kind of think about maybe some cases and whether we actually think this is true or not. So if we have the case where we have an AK, and AK is going to be equal to -1 to the power of K all over K is squared. And now, do we think that if the absolute value of this will also converge? Well, I think that is going to be true, because if I say AK absolute value, that will be equal to 1 over K squared. And look, this is going to converge, and also this one will converge too, because this is the p-series test here, and this we can either use the alternating series test, or after we prove this theorem, you can also use the absolute convergence test. And now when we're thinking about proving anything, we kind of want to think about, what do we already have? What tools can we use? So we're given some information. We know that this absolute value of K, the series of that will converge, but then we're assuming this converges, and we're going to actually be using the comparison test in this proof. So when you think of how are we going to prove this, it's always good to think of what you already have in your toolbox and how you're going to approach proving some of these things. So to actually use the comparison test, we need to remember the conditions, of course. So both an and bn need to be greater or equal to 0 for all n, and also an needs to be an needs to be less than or equal to bn for all n. And then if bn is convergent, so is an. If an is divergent, then so is bn. So since we want the convergent part, we can just cross this out. That's not going to be very useful. But we are definitely going to be using this comparison test in our proof, so you'll see it very shortly. Okay, now we're going to prove it. This is the second take, because last time I accidentally went off the screen as I was writing. So hopefully I get it this time before I get 3/4 of the way through the proof. So the first thing we're going to do when we write any proof is we're going to write a little PF. That was a horrible P, pardon my handwriting. And now we just discussed how we're going to use the comparison test within this proof. So the first thing we want to do is actually we want to show that the things we're going to be comparing are going to be greater than 0. So for every K, this is K, we can say that negative absolute value of AK is less than or equal to AK. Less than or equal to absolute value of AK. Which is pretty clear to see why, because this is going to be either negative or positive absolute value. If you know your absolute values, very clear. Therefore, again, pardon my handwriting. Now we want to make something so that there's a 0 involved. We want this all to be greater than 0, so that we can actually use our comparison test. So we're going to be adding this negative absolute value, or we're going to be adding absolute value of AK to both of these terms here. So now we can say 0 is less than or equal to AK plus absolute value AK. And then we can also say less than or equal to 2 absolute value of AK. So now we have all these terms, and they're actually quite nice, because we are basically at our comparison test. We just need to show that this 2 times absolute value of AK will also converge, and then we can say that these terms here will also converge. So to do that, we're going to say that if the series of absolute value of AK converges, then we can also say that absolute value of 2 AK, which is actually going to be equal to 2 times series of absolute value AK, is also going to converge. And again, we can take this 2 outside and multiply it by every term in the series, so that's why that works. And now that we have that this term converges, it's actually super helpful, because look, all these terms are greater than 0, and we can compare this one, and that's a bulk of the bulk of the proof. So then we could say, then by the comparison test, since we've satisfied all of the I guess prerequisites for using it, so by the comparison test, oh man, got laggy on me. We can say that the series of AK plus absolute value of AK is going to converge. Pardon my handwriting, jeez. Okay, so that's useful. This whole thing here is going to be convergent. And now the question is, does that necessarily imply that AK is convergent? And the answer is yes, of course, but we need to show it formally. We can't be informal in proofs. So that's just horrible, since it does not like a C, I guess, since, oh, I'm just struggling all over here. The series of AK plus absolute value of AK is equal to the series of AK plus the series of absolute value of AK. Then we can actually say, well, we know this one here is going to converge, and this converges, so this also needs to converge here, is the idea of where we're headed with this. So we say, we know if it would like to write a little bit better, that'd be nice. Series of AK converges. And from there, we know that the normal series of just AK with no absolute value also must converge. If it would like to write my G, that would be very appreciated. There we go. And now you can be really boring in a proof, and you could say QED, I could have my box of death and shade it in. But you know, I think those things are really quite boring, and honestly, I prefer writing a simple yay if my pen would work. Yay.